In this video, we will look at what happens if it is compounded more frequently. So let's stick to the same situation. Say we are going to the bank to get a CD, which we're going to invest $10,000 at a 3% interest rate over 4 years. Um, in that time, we're not going to be able to access our money. Um, but usually you can, but there'll be a fee. But let's assume that it's being compounded monthly instead of annually. And compounding monthly is the most common type of compounding because a lot of financial transactions are done on a monthly basis. Like, for example, home loans or car loans or credit cards, because usually you get every month there's a bill and it's like you need to pay this much of your loan off. And basically the balance is recalculated on a monthly basis, which just means that it's always being compounded on that monthly scale. And another difference about loans where you're paying them off on a month by month basis is they do work using a different formula than these, because these formulas are seeing what will happen if the balance, if it's never changing, if it's just like an upfront investment, what happens over time. But if you're simultaneously investing more or paying it off, it will also factor into the growth. And there's some more complex formulas for figuring those things out, which we'll talk about briefly. We'll look at using them, but we're not going to necessarily get into the math behind them because it is a little bit beyond the scope of what we need to do in this class. But anyways, let's do the same situation but monthly. So basically the only difference here is going to be n, the number of times compounded. And monthly just implies that, each month, which obviously there's 12 months in the year. So in this case, we're going to be compounding it 12 times per year, which is what's going to be our n. And in the compound interest formula, which is the exact same as above, we're going to start with the principal, multiply by 1 plus the interest rate. But the difference here is that it's going to be divided by the number of times it's compounded, which I'm changing to 12. And otherwise, we're using all the same parameters. So 4 years, 3%, $10,000 principal, and here we go. And also, if to calculate the future value, you could just memorize a formula or, look it up if you were, forgot it. But you could always just type this into a calculator. So I wanted to show you, well, we could just type this into a calculator. I do actually want to talk about the sense of what this formula is doing. But if you're typing it in, just make sure that the entire exponent, what I recommend is if you're using a more basic, like a scientific calculator, you want to calculate each of these things separately, like figure out exactly what the base of the exponential expression is and figure out the exponent first, then do all the math at once. Because some calculators don't necessarily do the order of operations correctly, but if you're using like a graphing calculator or more advanced calculator, you should just be able to type in the whole formula and come up with the answer. And so that's going to give us approximately $11,273.28, which is a little bit more than if it were compounded annually versus compounded monthly. But why? So what is this math? What did we just do? Let's look at this a little bit closer. And basically, one of the differences when it's compounded more than once per year is that, like in this case, it's compounded monthly. So what that's implying is that every single month, they're going to look at our new balance of our account. And if I think about what this 0.03 divided by 12 is doing, let's type that into our calculator. That's going to be 0.0025, which is 0.25%. So let me go ahead and write this all out in the formula. Just sort of, basically I'm going to have 1.0025, and that's going to be raised to the 48th power, which is just 12 times 4. Notice that what appears to be a little different about this is instead of growing by 3% every year, it's actually growing by this amount instead. And basically, if it's compounded monthly, every month it's not going to grow by 3% because the annual rate is 3%, not the monthly rate. So what this is sometimes referred to as the periodic interest rate or the monthly interest rate, which is basically this 2.5%. And right, if I multiply by 100, I can convert it back to percentage form. Sorry, I said 2.5, I meant 0.25%. And basically every month it will be growing by 25%. And then if I'm looking at the exponent, which is now significantly greater than 4, notice that over 4 years, if I was thinking about every single growth period in that 4 year thing, if it's happening every month, well, it's 12 times per month over the course of 4 years. That's a total of 48 times incrementally over the 4 years. So basically, every month it's growing by 0.25%, and there's 48 months in 4 years. So if it's growing by 0.25%, every month for the 4 years, that this is exactly what's going to happen. It's going to, it's going to exponentiate, and that's what our formula is calculating, is what is the net effect of that transaction, which which calculates, I'm starting with $10,000 and every month it's growing by 0.25% over the course of 48 payments. And sometimes the exponent here, which is n times t, is called the number of periods in the account. Basically, it's always going to be your time frame in years times the number of times compounded, which, like mathematically speaking, this is a much more difficult calculation, but at the end of the day, it yields a fairly similar result, just a little bit more, because as it compounds, it grows a little bit faster, and that's why when it's compounded monthly, it grows faster than compounded annually as well.